I'm going to cover heat and temperature, states of matter, specific latent heat and specific heat capacity, and stay to the end when I'll look at a typical 6-mark calculation. We're going to use the terms heat and temperature, so let's be clear about what these terms mean. Heat is a form of energy and it's measured in joules. Temperature is a measurement of how hot something is, and that's measured in degrees Celsius or sometimes Kelvin. A quick example might make this clear. This lit match has a high temperature but not much heat energy. This glass of water has a lower temperature but more heat energy. I can show this by dropping a lit match into the water. The heat energy from the match is now in the water and the temperature of the match has dropped a lot. The temperature of the water, though, has hardly increased at all. Temperature is due to the mean kinetic energy of the particles. There's a lot more particles or molecules in the water than there are in the match, so that heat energy has to be spread amongst more particles and therefore they get less kinetic energy each, so the temperature does not rise as much. When we apply heat energy to a substance, one of two things can happen. Firstly, as we've seen, the temperature could increase. Secondly, it could change state. Take a look at this graph. Energy is being applied constantly to the water, but there are two areas on the graph where this does not result in a change of temperature. That's because energy is going into breaking the bonds in the molecules and the state is changing. Firstly, it's going from a solid to liquid, and then it's going from a liquid to a gas. In a solid, the particles are held in fixed positions and can only vibrate around those fixed positions. This means that a solid is a fixed shape and a fixed volume. In a liquid, the particles are still held together, but not as tightly, not as firmly, and they can slip round each other. That means a liquid doesn't have a fixed shape, but it still has a fixed volume. In a gas, the particles are free from their bonds and can move around and fill the container that they're in. That means a gas doesn't have a fixed shape and doesn't have a fixed volume. So we said that there's an energy change when the temperature of a substance changes, and an energy change when the state of a substance changes. The total internal energy of a substance is the total kinetic energy of all the particles plus the total potential energy of all the particles. The kinetic energy is the movement of the particles, and that tells us how hot something is. The potential energy of the particles is the energy stored in the particles, and that depends upon which state the substance is in. Let's look at energy changes when we change temperature. The amount of energy required to increase the temperature of a substance depends upon the mass of the substance, the change in temperature, and what the substance is made from. So we can put this into an equation where delta E equals mc delta theta. That's where delta E is the change in energy, delta theta is the change in temperature, m is the mass, and c depends upon the substance itself. It's what we call the specific heat capacity. The specific heat capacity of a substance is defined as the amount of energy required to raise the temperature of 1 kilogram of something by 1 degree C. That's a definition that you need to learn, and it can be shown by rearranging the equations. So C, the specific heat capacity, equals delta E, the change in energy, over the mass times the change in temperature, where m is 1 kilogram and the change in temperature is 1 degree C. The units for specific heat capacity are therefore joules per kilogram per degree C. Substances with low specific heat capacities, like metals, don't take much energy at all for their temperature to increase quite a bit. Water has one of the highest specific heat capacities, which is why it takes so much energy to heat up a bath of water. Let's look at a quick example. How much energy does it take to heat up 1.5 kilograms of water in a kettle by 70 degrees C? The specific heat capacity of water is 4,200 joules per kilogram per degree C. As always, we start with the equation. E equals mc delta theta. We're trying to find the energy, so that remains as E. The mass m is 1.5 kilograms. The specific heat capacity of water, C, is 4,200 joules per kilogram per degree C. The change in temperature is 70 degrees. Multiplying all those together, we get 441,000 joules. We use the specific heat capacity formula when energy is required to change the temperature. When there's a change in state, we look at a slightly different property of materials. This property is called the specific latent heat. The amount of energy required to change the state of a substance depends upon the mass of the substance and the specific latent heat. The equation looks like this. Delta E equals mL, where delta E is the change in energy, M is the mass again, and L is the specific latent heat. To confuse matters a little bit, each substance has two different specific latent heats. One is for when it turns from a solid to a liquid, which we call the latent heat of fusion. The other is when it goes from a liquid to a gas, which is what we call the latent heat of vaporization. To help prevent us getting confused, we can use little subscript letters to identify which is the latent heat of fusion, which we use little f for, that's solid to liquid, and which is the latent heat of vaporization, we use a little v for, and that's from liquid to vapor or gas. The unit of specific latent heat is just joules per kilogram, because the definition of specific latent heat is the amount of energy required to change the state of 1 kilogram of a substance. Again, learn this definition. Importantly, temperature doesn't come into this equation, and that's because as something is changing state, its temperature remains constant. Let's look at an example. What is the energy required to boil 1.5 kilograms of water until it all turns into water vapor? The specific latent heat of vaporization of water is 2,260,000 joules per kilogram. Let's start with the equation again. Delta E equals ml subscript V, which is 1.5 kilograms times 2,260,000. Plugging that into our calculator, we get 3,390,000 joules. How does boiling 1.5 kilograms of water compare with melting 1.5 kilograms of ice? Well, water has a specific latent heat of fusion of 334,000 joules per kilogram. So, delta E equals ml subscript F, which equals 1.5 kilograms times 334,000. Plugging that into the calculator, we get 501,000 joules. You can see there it takes a lot more energy to change the 1.5 kilograms of liquid water at its boiling point into water vapor than it does to change 1.5 kilograms of ice at its freezing temperature into 1.5 kilograms of liquid water. Before I work through a typical 6-mark question, I want to take a moment to remind you that there's some practice questions with worked answers all available to download for free from my website. There's a link to that in the description. I'd also appreciate it if you could take a moment to like and subscribe. That helps me produce more and more of these free resources. I read all comments too. Right, here's the 6-mark exam question example. 12 kilograms of liquid water at 60 degrees C is heated by 6 megajoules of heat energy. What mass of water is vaporized? The specific heat capacity of water is 4,200 joules per kilogram per degree C, and the specific latent heat of vaporization is 2,260,000 joules per kilogram. First, we need to work out how much energy it takes to heat the water to the boiling point of 100 degrees C. Because it's a change in temperature, we're going to use the specific heat capacity equation. So, delta E equals mc delta theta. We're talking about 12 kilograms, and the specific heat capacity is 4,200. Temperature change can be found from 100 degrees minus 60 degrees, which is 40 degrees. We put all that in our calculator and we get 2,016,000 joules. So how much energy have we got left? Well, we take our 6 megajoules, which is 6 million joules, and take away the 2,016,000 joules required to heat the water, and we get 3,984,000 joules. So how much water can be vaporized with that energy? We use the specific latent heat equation to find out, because we're changing state. So delta E equals ml subscript V. So that's our energy, which is 3,984,000 joules, equals m for the mass we're trying to find out, times 2,260,000, which is the specific latent heat of vaporization of water. Rearranging that equation, we get our 3,984,000 divided by 2,260,000 equals m. And putting that in a calculator, we get 1.76 kilograms. So only 1.76 kilograms of water of the 12 kilograms would actually evaporate. Heating water and changing the state of water takes a lot of energy. Maybe if you found this useful, you want to look at another video like that one.